Great. So our next speaker is Iglesias. She is going to talk about the vertical distribution of mesopelagic fishes in the California current and the responses to heat waves. So without further ado, have Ili take it away.
Great. Thank you so much. I really appreciate the invitation, and thanks to Tim for a great talk and for being here today. I'm grateful to have the chance to share with you a little bit of the results from some of my dissertation work. And this work that I'll be presenting today, I want to first acknowledge my co-workers, also my co-workers, but also my co-authors, who are really instrumental in this project, and that's Jerome Fischer at UCSC, Jared Santora, and John Field at NOAA. This paper is available publicly if anyone's interested, as well as my probably terrible code and all of our processed acoustics data. So just want to start by acknowledging that. I want to talk for a moment about the motivation for this work. I think in the media and even in the way that we portray our research, so often the deep pelagic and the mesopelagic zone in particular is seen as something other than what we're familiar with. It's always, how weird things are, how different, how removed. And I think one of my central motivators for my work has always been to show that it's actually a very integrated, important part of just the bigger ocean ecosystem. So when we think of mesopelagic, we put these nice little borders on it between 200 and 1,000 meters. But of course, for a lot of these organisms, they don't follow our rules. And if you were to look at the same ecosystem during the daytime or during the nighttime, for example, a lot of these organisms are in direct contact with the epipelagic zone, for example, when these organisms undergo diel vertical migration. And we know that this is a direct way that mesopelagic organisms are being affected by shallower surface waters, but the motivation for this project was to see whether or not there's indirect effects as well, and whether changes in the surface conditions could actually have an impact on the distribution of mesopelagic organisms during their daytime deeper realm. So for those that are not familiar, we had a large marine heat wave event. It was also referred to as a blob, and this picture kind of gets at why. It was a large area of anomalously high, mainly surface intensified warm temperatures. It started in 2013, but when I referred to the heat wave subsequently in this talk, I'm referring to specifically 2015 and 2016, which is where the most pronounced effects of that warming were in the Central California current area, which is where I was doing this study. And perhaps I wouldn't describe it quite so simplistically as the winners and losers of this, but there's been a lot of work, and kind of highlighted in this figure on the right, that showed that during this time, these increased temperatures had profound effects on the epipelagic community. There were toxic algal blooms that led to fisheries closures. There were entanglements of humpback whales and crab gear. There was huge reductions in some cases of some of the primary base organisms in the food web, and there were a lot of shifts in species north to south or onshore and offshore. And this has been really well documented, and while it varied by organism, overall it had a profound effect on epipelagic communities, but it's less clear whether or not this surface warming event had an effect on the mesopelagic community, which again is still going to be responding to what's happening directly above it. So to address this question, I used data from the NOAA National Marine Fisheries Service Rockfish Recruitment and Ecosystem Assessment Survey. This is an annual survey that occurs in the spring, so to correspond with upwelling along the California coast. This is a map of California on the right, and the survey covers the entire range from the Oregon to Mexican borders, but we focused on the central core region, which is what I'll be talking about today, and those waters that were deeper than 725 meters, so off the shelf, even though a lot of this survey is closer to shore. And as we know, mesopelagic organisms are difficult to study because of their daytime depths, and acoustics provide a method, not unflawed by any means, for sampling these deeper regions. We used acoustic data from an Simrad EK60 echo sounder, which collected multi-frequency data. I'm only going to be talking about 38 kilohertz today. But we also had some other frequencies available, just not in all years. We only looked at daytime data because we wanted to look at the mesopelagic vertical distribution at its maximum, as opposed to as mentioned, while they were migrating up in the surface, where it's difficult to disentangle from other epipelagic forage species. Again, we looked at those depths that were greater than 725 meters, and we defined the mesopelagic zone in this study as about 175 meters as the upper limit, which had been shown in previous work to be the start of the main scattering layer, to about 675 meters. And below that depth, we started getting a lot of noise. So we didn't actually look at the deeper scattering layer, which occurs deeper than that. So today I'll be talking about the main scattering layer. I'd also like to point out that I will be mentioning mesopelagic fishes, but just every time I say that, just assume there's a little parentheses around fishes, because there's a lot of sources of uncertainty in acoustics data. We applied a threshold of negative 75 dBs to these data, which is equivalent to about the backscatter you would estimate from 1 mictophed and about 1 meter cubed volume of water. But of course, that doesn't mean that we didn't include other things as well. I want to touch on that just a little bit more so that you can have an appreciation for some of the uncertainty in acoustics data, while still saying that I think, we get a great opportunity to look at some of these large scale changes between years. So acoustic backscatter, essentially on the vessel, you can think of this, the vessel at the top. This is called an echogram, and you can think of the little boat traversing this area. So in this case, our x-axis is going to be distance. That could also be time, but it's a combination of those for us, and then range is on the y, so this is depth. And as the boat is traversing the water column, you're sending out sound from the bottom of the vessel, and that sound gets reflected off of the organisms in the water column. Things that have a similar density to water do not reflect a lot of sound, as you can imagine, but those things that have a different density, so something that's like a shelled organism, for example, or specifically in our case, a swim bladder for a mesopelagic fish, reflects that sound back to the boat, and we call that acoustic backscatter. And something that has air bladder tends to reflect more sound, so it has a higher backscattering intensity than something that does not. And for 38 kilohertz data, which is what we used, most of that backscatter is going to be from mesopelagic fishes. But again, there's quite a few caveats with acoustics data, including not all mesopelagic fish have swim bladders. Many of them don't have a swim bladder at all, or they have a swim bladder at a specific life stage that ingresses with fat as they age. You also have an issue just sampling to mesopelagic depths with beam spreading. So you're sending this little ping of sound from the vessel, but it has to traverse hundreds of meters of water to get to the mesopelagic zone. And in so doing, it's interacting with the water and spreading. So we use volume spreading, in this case, volume scattering to describe this community acoustically. There's also challenges with ground truthing because it's difficult to get nets to these depths. The survey that I've mentioned does trawl operations at 30 meters because they're targeting juvenile rockfish. So we don't have good ground truth data. So with all those caveats in mind, I just want to make a final note to say that I'm well aware that the deep scattering layer is not just fish. That's certainly the focus for today, but it's a rich, diverse assemblage of organisms, as we all probably know, because we study the system and it's really unique. But that's going to be the focus for today. So to process these acoustic data, these data were collected on 2 different vessels and in a lot of different conditions. This is an example of a messy echogram on the bottom left here that needed a significant amount of processing in order to get at that scattering layer. So we used calibrated data. These data were calibrated annually. We accounted for varying ocean conditions by correcting for sound speed and absorption coefficient using CTD data. So the vessel also deployed CTDs, and we used the 3 nearest CTDs per day in space and time to account for that. I manually edited bottom lines and removed false bottoms. And we also filtered for impulse noise, attenuated signal, transient noise, and background noise, which are all sources of error in acoustics data. And we processed everything in the same way. We removed bad data regions, and I calculated 2 metrics for this, which were a mean volume backscatter, or SV in this case, and center of mass depth, which is the weighted mean depth based on that backscatter from SV. So if we just look at all of the data, this is Each one of these years represents about 6 weeks of data from the survey. And if you just take like a first pass at it, you can kind of see that a pattern emerges where 2015 and 2016, which for reference are the 2 years that we consider to be the most impacted by the marine heat wave in the Central California current region where we were focused. You can see that it looks a little bit deeper, but before we could more formally analyze this, first had to deal with one more caveat of acoustics, which is autocorrelation. Acoustics data are incredible in that you collect high resolution continuous data while underway on the vessel. But one of the drawbacks is that you collect continuous high resolution data that has its own inherent spatial autocorrelation. So to address this, we calculated Moran's I with increasing distance, which looks at, that correlation spatially amongst the data. You can also think of this in terms of like a patch size, essentially. For each year of our study, we found a mean spatial autocorrelation distance of about 25 kilometers. So after that, there was more spatial independence. So we regridded everything by about 25 by 25 kilometer grid cells. So everything I'll be sharing after this has been regridded. So if we explore our initial question of whether or not there's a change in the depth distribution of mesopelagic fish during this time, this is a center of mass depth. Again, that's a weighted mean depth. It's weighted by acoustic backscatter for each year that we examined from 2013 through 2018. The years 2015 and 2016, which were the most pronounced of the heat wave, you can see that there's a significantly deeper distribution of mesopelagic fishes during this time. 2013, which was the first year of our study, the center of mass depth was 256 meters, which was over 100 meters shallower than both of the years during the heat wave. So that main scattering layer was shifted at least 100 meters deeper than that initial year in 2013. 2013 is defined as a really strong upwelling year, so it's not necessarily the average preconditions, but there was quite the contrast between those two. 2014 and 2017 were kind of intermediary, and it follows generally a parabolic curve where the deep scattering layer was fairly shallow in 2013 and seems to be resuming in that direction in 2018, but 2015 and 2016 were significantly deeper. If we examine the whole distribution of these depth values, on the y-axis is the center of mass depth represented in meters. You can see that in 2015 and 2016, which were these two warm colors, so like the orangey on this plot, you can see that not only was there a shift deeper during the heat wave, but that the whole spread of depths that were being occupied was condensed during that time. In some of the other years, you can see multiple peaks at different depths, but during 2015 and 2016, there was a deepening and a narrowing of that range that was being occupied of the water column. The second question that was related to the outcome of the first was which oceanographic conditions might be responsible for this shift. And to explore this, we use CTD data collected on board the Rockfish Recruitment Ecosystem Assessment Survey. Again, these are 25 by 25 kilometer grid cells, which corresponded to the plus signs in there are CTD deployments. We also used as an indication of light, we used satellite data, used 8-day composite scientific grade Aquamodus data for that. Because our light sensor was only working in a couple of the years. You know how it is with CTD and ship deployments, although we didn't lose the sensor like Jim had mentioned, so we consider ourselves lucky. But in this case, we use CTD and a combination of satellite data to look at which oceanographic conditions might be driving this observed shift that we saw during the heat wave years. We used a generalized additive model to examine the functional relationship between these oceanographic conditions and found that light acoustic backscatter, so that was mean volume backscatter, and dynamic height anomalies explained about 80% of the variability in center mass depth. And the relationship between center mass depth and light was most straightforward. It was a almost linear relationship where increasing light led to increasing center of mass depth. Acoustic backscatter, increasing acoustic backscatter led to increasing center mass depths up until a point, it looked like about 68 dBs, that kind of plateaued. And then dynamic height anomalies, which we consider to be a proxy for upwelling intensity. If you move to the left on that plot, otherwise upwelling increases, the center of mass depth decreased. So with more upwelling, once again, the center of mass depth decreased. So if we take all of these variables together, light, backscatter, and dynamic height anomalies, what we think is happening during this time is that there was the surface intensified warming in the water column, which led to increased stratification. And even though there were, in some cases, upwelling favorable winds during this time, the amount of upwelling habitat was compressed close to shore because of that stratification and this warm lens of water on the surface. And because of that, there were two documented changes. One was that the fog during this time actually decreased because there was less of a temperature gradient between the atmosphere and the surface of the ocean. So there was less fog, so more light reaching the surface of the water. And then because that upwelling habitat was compressed near shore, there was less nutrients available for primary productivity, which led to a decrease in overall productivity during this time, which then allowed that increased light to penetrate deeper into the water column. And the effects of those combined, we think mesopelagic fish responded to by descending deeper into the water column. So the surface conditions during this time, during the heat wave, led indirectly to effects in the vertical distribution of mesopelagic fish. And this is not new. There's been a lot of previous research which has shown that mesopelagic fish in particular are very responsive to changes in light. Even during like a passing storm when it's cloudy, they found that there's an adjustment of the depth of the deep scattering layer during that time. So this is not new, but I think it sheds light on the fact that what's happening in the surface is not disconnected to mesopelagic communities and that they're going to be responsive to that, to those changes as well. So when we kind of zoom back out and think about what the ecosystem level effects of this might be, one thing, oh, sorry, I didn't realize that was an animation, sorry. One thing that we can think about is how this may affect predator populations. And I think I saw Rachel on here on the call, which I'm really grateful for because I'm referencing her work here, which has shown that northern elephant seals forage deeper during this marine heat wave, and they're a known predator of mesopelagic fishes. And so it's possible that they're having to forage deeper, which may, exert energetic costs to these higher level predators who are seeking prey at deeper depths. Also, the bottom figures are ones that I created using downscaled climate projections for the California current. And if we predict how things are going to change in the California current out to 2100, it looks like chlorophyll is going to decline. There's a lot of uncertainty, certainly. This is on ensemble of 3 downscaled climate projections shown here. But if we think about how this might affect the availability of mesopelagic habitat into the future, if productivity is declining and there's potentially more light reaching mesopelagic depths, which on the plot on the right is isolume depth, which slightly decreases, and combined with potential shoaling of low oxygen conditions, which is that bottom orange line, then it's possible that in the long run, mesopelagic fish are going to be impacted by this by the end of the century as well. So I think that's it for me on time. I also just wanted to make a note that I'm going to be continuing this work. I just started a postdoc position with Dr. Anela Choi at Scripps, and she has done a phenomenal job of collecting data at depth discrete levels using a mock nest. So I'm hoping to pair that up with some EK80 data and get a finer resolution of the acoustics data and look at what's actually creating this backscatter instead of just hoping it's mesopelagic fishes. And also trying to link that up with more fine scale resolution oceanographic variability. So with that, stop sharing and see if I can bring you guys back.
Thank you so much, Illy. That was really great. And that's exciting that you will now be using mock-nest data to sort of ground truth some of that. So yeah, exciting stuff. So does anyone have any questions about any of either for Illy or Jim? Well, I'll start off just for a question with Illy. What did you see any changes in migration patterns at all with the acoustics, or was it really you were just focused on the depth of that scattering layer?
That's a great question. Yeah, for this analysis, we just looked at daytime data. just the way that the survey works is we typically trawl at night, which is really noisy, and we're pretty much stopped. And so that data wasn't usable to actually examine some of those more fine scale vertical distribution patterns. But I think that would be a great thing to look at.
Trying to figure out where my hand is.
Yeah.
Great talk. I really think that somehow acoustics and what you're doing actually has a key to answering where this added carbon flux is coming from that we've observed. And if there's any way that you can actually look at, there was a lot of acoustic data taken on the cruise that Hannah Bourne went to see, and I went to see on, that's P1706. If you ever have a chance, please do that.
Thanks so much for your comment. Yeah, if you ever want to follow up, I'd be happy to talk. I think a combination. I was thinking the same thing. There's a lot of overlap.
Hi, Ellie. That was a really great talk. Thank you so much. I'd love to talk to you more because we're my lab mate Arena is also on the call, and we think about mesopelagic fishes a lot. And I was also just commenting that we have actually a lot of light level data that's collected off of our animals, which we have dramatically underutilized so far because we're usually focused more on the behavior side of things. In addition to the CTD data that some of the animals are collecting while they're out as well. So that might be interesting to think about more for the future.
Oh man, thank you for your comments. That's so fascinating. I mean, your work is very inspiring. It was really nice to think about how this affects different trophic levels. So yeah, if there's an opportunity to work together, I would love to just hear your thoughts from the predator perspective.
Yeah, definitely. We have lots of thoughts. We'll be in touch for sure.
Good. Sounds great. I look forward to it.
Great. Any other questions for Illy? No? I do have a question for you, Jim. I was wondering if you had any comments about seasonality and how that might affect, I don't know, if it could affect the kind of question that you're seeing in the Southern Ocean about that, high concentration of PIC that you're seeing in the sensors that you're not seeing in the samples, and wondered if different times of year, yeah.
Well, you're talking about a ship crossing the Antarctic polar front between Christmas 2023, 2022, and January 2023. The interesting thing is that this birefringence interference is there. There's a bias in the satellite data. There are actually two satellite algorithms. I only showed data from one, but there are two. And the other one, which is supposed to be the quote unquote improved version, is even higher in terms of discrepancy. The only way I know how to resolve the seasonality issues is to repeat the kind of work that we did during SOFEX, where we launched 4 carbon explorers in the Southern Ocean, north and south of the polar front, and let them go. One of them died quite quickly, but 3 went for a year and a half and went through the Antarctic winter. And so that paper was really interesting for me to come back to. So yeah, I'd really love to get a chance to look at the temporal domain. The other thing is there might be some merit in actually, and I've suggested this to Yun-Hao Lee, is to actually just do retrievals for the areas that we refer to as hotspots, like the equator and south of the subarctic polar front, and also north of the Antarctic polar front, south of the subarctic front, and north of, yes, and just sit there and do several annual cycles and see what comes out. what Yun Hao has found is that the satellite retrievals, even though they come back with valid pixels, they're somehow masking, even if you north of the polar front, there are cases where you get an anomalously high retrieval, and the multiple satellites disagree with one another. So we don't understand that, but it seems that we're working towards coming up with a rule set that if 4 satellites see the same thing, it's believable. If 4 satellites disagree with one another, even though their overpasses are within hours, then that's something else to do. If you're interested in hearing from Yun Hao, I'll forward you his email, and he'd be really good at explaining what he thinks is going on with the satellite retrievals. Because I've sort of stolen some of his thunder by talking about the results. So yes, we'd like to put ocean carbon observers in the Southern Ocean. And if anyone has a ship program deploying bioargo floats and otherwise, we'd certainly be willing to figure out a way to writing proposals to collaborate.
That will be good food for thought for us. Great.
Yeah.
Thank you so much. All right. Well, it looks like, does anyone have any last remaining questions? No? Well, in that case, we are about out of time. So I'd like to thank you both, Illy and Jim, so much for talking this month. Really fascinating talks. And for everyone else tuning in. Thank you so much. And I hope everyone has a good holiday break, and we'll be back next month with the next seminar series in the sort of European time zones. So yeah, great.
Yeah.
Thank you
Please
so much
let
for
me
the
know.
invite and for organizing.
And thank you very much. I appreciate it.
Thank you, Jim. Lovely to meet you both.
Take care.
Mhm.